There's this incredible silent system running the show inside all of us. It's basically an autopilot, keeping our bodies humming along without us even having to think about it. Today, we're going to pull back the curtain on how this system works, and even cooler, how modern medicine has figured out how to take the wheel.
I mean, we've all been there, right? That sudden thump, thump, thump of your heart before you have to speak in public, or that sleepy, heavy calm that washes over you after a huge holiday meal. Those feelings aren't just random. Nope, that's your internal autopilot, reacting to the world. So what's actually pulling the levers behind the scenes?
Well, that command center is called the autonomic nervous system, or the ANS for short. This is the part of our nervous system that handles all the critical stuff we don't consciously control. Everything from your breathing to your digestion. You can think of it as the unsung hero, working 24/7 to keep you in perfect balance.
Okay, so to keep everything balanced, this autopilot needs two kind of opposite controls. And honestly, the best way to think about them is as a gas pedal and a brake for your body.
So these two branches are the sympathetic and the parasympathetic systems. The sympathetic system, that's your fight or flight response. It's the gas pedal revving your whole body up for action. And the parasympathetic system is the opposite. It's your rest and digest mode. It's the brake, telling your body, hey, let's calm down, conserve some energy, and recover.
In this chart, it lays out that push and pull relationship perfectly. Just look at the heart, for example. The sympathetic system slams on the gas, jacking up the rate, while the parasympathetic hits the brakes, slowing it right down. Or check out the lungs. The sympathetic system opens up the airways, that's bronchodilation, to suck in more oxygen, while the parasympathetic does the exact opposite. It's just this constant, beautiful balancing act. And yeah, the contrast is pretty stark when you see it side by side. On one side, fight or flight is ramping everything up. Heart's pounding, pupils are wide, digestion is on hold. On the other side, rest and digest is flipping the switch. Heart slows down, pupils get smaller, and digestion kicks into high gear. It's literally gas pedal versus brake pedal. So how does the command center actually send out all these orders? It's not using wires like you might think. Nope, it uses these unbelievably fast chemical messengers.
Now, the fancy term for this process is neurohumoral transmission. I know, it sounds super complex, but the idea is actually really simple. One nerve cell just releases a chemical, and that chemical travels to a target cell to deliver a message. It's just like sending a biological text message, and it happens in an instant.
And every single one of these texts follows a few basic steps. First, that chemical messenger, the neurotransmitter, is created and stored, ready to go. Then, when the signal comes, boom, it's released. And finally, it travels across a tiny gap and binds to a specific receptor on the target cell to deliver its instruction. Done.
So what are these messengers for the fight or flight system? Well, you've definitely heard of the main one, epinephrine, which, we all just call adrenaline. That, along with its cousins norepinephrine and dopamine, are the chemicals that give you that incredible rush of energy when you're stressed or excited.
All right, so let's recap. We've got this autopilot system with a gas and a brake, and it's all controlled by chemical messengers. This is where things get really cool because this is where pharmacology comes in. We've literally figured out how to hack this system.
It got pharmacologists thinking this really powerful question. Wait a minute. What if we could design drugs that either press the gas pedal for us, or what if we could block that gas pedal from being pressed in the first place?
And the answer, of course, is a huge yes, we absolutely can. The first type of drug are called sympathomimetics, but let's just call them mimickers because it's way easier. They're designed to act just like our natural adrenaline, binding to the exact same spots and triggering that fight or flight response whenever we need it. In short, they press the gas pedal for us.
And then on the flip side, we have sympatholytics, or blockers. These drugs also bind to the same spots, but they're like a key that fits in the lock but just won't turn. By just sitting there and occupying that space, they physically block our natural adrenaline from delivering its message. They're basically easing our body's foot off the gas pedal.
I know. This might all sound a little bit abstract, but stick with me, because understanding this system is the key to countless modern medicines you'd find in any pharmacy today. Okay, so here's where it gets really, really precise. Those docking stations, the receptors, they aren't all the same. We have different types in different parts of the body. For example, beta-1 receptors are mostly found in the heart, while beta-2 receptors are packed into the lungs. And that specificity is exactly what allows us to create these incredibly targeted drugs. So let's look at a classic real-world example of a mimicker drug at work, an asthma inhaler.
So when someone has an asthma attack, their airways are constricted and they need them opened up, like right now. The inhaler delivers a drug that mimics adrenaline. But here's the clever part. It's a specific mimicker. It's designed to target those beta-2 receptors that are all over the lungs. It presses the gas just for the airways, causing them to relax and open up, but without unnecessarily revving up the heart. So smart.
Okay, now let's flip it and see how a blocker drug can be just as much of a lifesaver.
For someone with high blood pressure, for example, their fight or flight system might be putting a constant strain on their heart. So the solution is the exact opposite of the inhaler. We use a beta blocker. This drug specifically targets the beta-1 receptors in the heart. It blocks adrenaline from constantly pushing the heart too hard, which effectively eases off the gas and protects it over the long term.
And that's really the whole ballgame. It's so elegant when you think about it. By understanding the natural push and pull of our body's autopilot, this gas and brake system, we've developed tools to step in. We can now create drugs that either mimic our body's own signals or block them, letting us fix imbalances with incredible precision. I mean, think about that. We have literally learned how to grab the steering wheel of our own biology. It really makes you wonder, as our understanding gets deeper and deeper, what other complex system inside of us are we going to learn to fine-tune next?